I'm Professor Rad, and this is Precalc video 213, holes and asymptotes. So in this video, we're going to be looking at rational functions and trying to figure out when a rational function will have a hole and when it will have a vertical asymptote, a horizontal asymptote, or an oblique asymptote. So we're going to start out with some guidelines for finding holes and vertical asymptotes because there are similar issues when we find them. So if you'd like to pause the video here and write down these guidelines so you have them in one spot in your notes, feel free to do that. And now let's talk about what this all means. So holes. A rational function is going to have a hole if basically it's a factor that you canceled out of the numerator and of the denominator. So here it says if x minus a is a factor of both your numerator and your denominator, then that's where you're going to have a hole. So that would have been a factor you canceled out when you simplified the rational expression. So to figure out the y value of the hole, you're going to substitute that x value in to the simplest form version. So let's do a real quick like mini example of this. So let's say I have x minus 4 times x minus 2 over x minus 2 times x plus, I don't know, 10. We'll see if this works. So if I have this rational function, I notice that x minus 2 is a factor of the top and the bottom. So I can cancel that out and simplify to get x minus 4 over x plus 10. Now to find that hole, the hole is going to happen at 2 because x minus 2 was the factor we canceled out. So I'm going to have a hole with the x value of 2. To figure out the y value, I'm going to take this reduced or simplest form version and substitute 2 into that. If I try to substitute 2 into the original function, I'm going to run into a problem because I'm going to get 0 over 0, which is undefined. So that's why we're going to substitute into this function here. So we'll do 2 minus 4 over 2 plus 10. So that will give me negative 2 over 12, or negative 1/6. So this function will have a hole when x is 2, and the y value of that hole will be negative 1/6. Now we will be examining what this looks like graphically in a future video when we talk about how to graph rational functions. But essentially what's going to happen is you're going to have some curve that ordinarily would be doing something like that. And the hole happens with a little open circle there. So this rational function and this rational function are exactly the same, except one of them has the hole right here. So this one has a hole right here, whereas this one does not. This reduced form would have had a solid point if this was just the original function. So a hole can happen when your numerator and your denominator have a common factor. If the numerator and the denominator don't have that common factor, then factors of the denominator are going to be vertical asymptotes. So this is another place where your denominator would be 0. So that's why in our characteristics for our vertical asymptotes, we see that r of x is a rational function in simplest form. So we're already looking at a rational function in simplest form, so we don't have to worry about common factors between the top and bottom. So that function will have a vertical asymptote of x equals whatever, if that whatever is a 0 of the denominator. So as a real quick example here, let's say I have x plus 3 over x minus 2, x plus 5. So here our numerator and our denominator don't have any common factors, so it's in simplest form. So if I set each of these values equal to 0, I will get my vertical asymptotes. So here we have x is equal to 2 and x is equal to negative 5. Remember that a vertical line has the form x equals a number, so we do want to keep this x equals 2 and x equals negative 5. These would be our two vertical asymptotes for this function. Okay, we'll do some more examples of both of these in a little bit. But before we get there, let's talk about horizontal asymptotes and oblique asymptotes next, because those two are going to have some commonalities that are a little bit different from these two. So these are the indicators for a horizontal or an oblique asymptote. So if you would like to pause the video here and copy those down, feel free. And now let's go through them. So we're going to let r of x be our rational function p over q. If this is a proper rational function, meaning the degree of the top is smaller than the degree of the bottom, you will automatically have a horizontal asymptote y equals 0. Done. That's it. There's no more work involved. If you have an improper rational function, so if the degree of the top and the degree of the bottom are the same, or the degree of the top is larger than the degree of the bottom, then you have more work to do. So if r of x is improper, then what we're going to do is we're going to carry out the division p of x divided by q of x. If q of x is linear, then this is nice because we can use synthetic division. But if q of x is not linear, then we're going to have to use our long division process. We're going to ignore whatever remainder you get. The remainder is irrelevant in this case. Whatever the quotient is going to end up being your horizontal or your oblique asymptote, depending on what you get. Now, the reason that we're ignoring the remainder, I'm going to talk about this a little bit. So let's say you do your dividing, right? And you get something like x minus 5 plus, and then your remainder was like x minus 1, and you had divided by x squared plus 3. Again, I'm just making this up, okay? Sorry, you would get, let's say you got x minus 1. I don't know. Yeah, something like that. Okay, so in this situation, the reason that we can ignore this little remainder piece is because both a horizontal and an oblique asymptote explains like end behavior of your function. So you have like super, super big positive or negative numbers at the end of your rational function. So if I look at this for really big values of x, we're going to see that this ends up going to 0. It's so close to 0, we're going to treat it like 0, and so it doesn't impact our result. Here's why that happens. So what I'm going to do, it's going to seem weird at first. I'm going to divide each of these pieces by x squared. So I've got x over x squared minus 1 over x squared. And then in the bottom, I have x squared over x squared plus 3 over x squared. Bear with me, there's method to this madness here. Now, if I reduce these, this is going to give me 1 over x minus 1 over x squared. And this will give me 1 plus 3 over x squared. By the way, this is just like a little playing around with stuff. So I'm not necessarily going to ask you to do this, but this is some argument about why we can ignore this piece. So, so when I have this piece here, remember that x for an oblique or horizontal asymptote, x is really, really big, right? So think about what happens to the denominator of a fraction when the denominator is really, really big. So if you have like 1 over 2, you get a half. Okay, it's a fraction, not super small. But if you do 1 over 100, that's 0.01. So that's pretty tiny. If you do 1 over a million, now you have a bunch of zeros 1. And if you have 1 over a million, right? If you keep making your denominators huge, the fraction itself is going to get smaller and smaller and smaller. So it goes towards 0. So this 1 over x is going to go towards 0. This 1 over x squared is also going to go to 0. 1 just stays 1 because there's no x involved. And 3 over x squared, doesn't matter that the top is 3, you're still dividing by bigger and bigger and bigger and bigger numbers. So that's going to go to 0. So for really large values of x, you end up getting 0 over 1, which is 0. So when you have a really large value of x, this rational expression piece is going to become irrelevant. It's just going to turn into 0. By the way, this process of examining what's going to happen when x gets super large, key concept in calculus. So we're going to see little glimpses of that. This is a concept called limit. So we're going to see little glimpses of limits in this class, but we're not going to do them like, hardcore. You're going to see those when you get to calculus. So this piece is going to go away and we'll be left with just the quotient when we divide. So big picture of this whole deal is if you want to find the horizontal or oblique asymptote, carry out the long division, ignore the remainder, just focus on what your answer was. And that will be either the horizontal or the oblique asymptote. So let's do some examples of finding asymptotes and practice all of these concepts all together. For this example, we're going to be finding all of the asymptotes. So all vertical asymptotes, horizontal or oblique, for these two functions, f of x and g of x. So let's look at f of x. We'll work through that one first, and then we will work through g of x. So in order to find asymptotes, it's going to be helpful for us to have numerators and denominators in factored form so we can eliminate any option of a whole, right? So when I look at f of x, the denominator is already in factored form. We have x minus 5 to the 4th. So that part's good. For the numerator, I would need two numbers that multiply to 1 and add to -1. Can't think of anything offhand. So I'm going to check the discriminant real quick, see if I get a positive or a negative. So b squared is 1 minus 4ac. Oh, yeah, that's going to be negative. So that means this doesn't factor over the reals. Okay, so this is already in simplest form, no common factors. So to find the vertical asymptotes, remember that vertical asymptotes, you set the denominator equal to 0. So I have x minus 5 to the 4th equal to 0. Now, the only way this is going to be 0 is if x minus 5 itself is 0. So that means that x is going to have to equal 5. So this will be our vertical asymptote for this function. To find horizontal or oblique, I'm going to check first if it's a proper function or if it's improper. If it's a proper function, then it's going to be 0. And if it's improper, then I have to do some division. So the degree of the top is a 2, and the degree of the bottom is 4. So this is proper, which means we have the horizontal asymptote y equals 0. All right, so this is about as good of an example as we're going to get. So we didn't have to do any factoring, and we had proper, so we didn't have to do any dividing, and we can find our vertical and our horizontal asymptotes. Easy peasy. So I'm betting, B is not going to be so easy. So let's walk through that one. So first things first, I notice that the numerator and denominator are not factored. So pause the video here and practice factoring, and I'm going to do the same. And in a moment, you'll see the factored form on the board. All right, so how did you do with your factoring? So this is my factored form. For my numerator, I got x plus 1, x minus 1, x plus 4. And for my denominator, I got x plus 3, x minus 2. So the denominator was not too bad because it was a nice quadratic trinomial. So we have to multiply to -6, add to 1. So that gave me positive 3, -2. For the numerator, I noticed that grouping was going to work because we had a coefficient of 1 and 4 and coefficients of 1 and 4. So I took a chance on grouping and it worked out fine. And then I got this difference of perfect squares, x squared minus 1. So that's where the x plus 1, x minus 1 came from. Great, so this one is in factored form, and I noticed that the top and the bottom don't have any factors in common, so it's not going to simplify anymore. So that means we can go ahead and find our vertical and horizontal or oblique asymptotes. So for the vertical asymptote, I'm going to do that over here. So for the vertical asymptote, you set your denominator equal to 0. So in this case, we're going to set each of these factors equal to 0 and solve. So we have x plus 3 is 0 and x minus 2 is 0. So this means x is -3 and x is 2. So these will be our two vertical asymptotes for this function. So you can see that sometimes a rational function will have more than one vertical asymptote. That's totally fine. You can have more than one vertical asymptote. You can have more than one hole in your function. All sorts of things can happen. So that's the easy one. Now we have to do the horizontal or oblique. And for this one, I notice my top has more factors than the bottom. And the degree of the top is bigger than the degree of the bottom, which means we're going to have to do some long division. Even worse, the denominator is quadratic, so we're going to have to use long division. You can't, just jump right to synthetic. So I was leaving space to do the dividing, but I don't even think that space is going to be enough. So I'm going to clear some space on the board. Goodbye, work. We hardly knew ye here. And let's do some long division. So when you do the division, you want to use the unfactored form. So we're going to go back here. The numerator goes in the box. Making sure if I'm missing a term to put a placeholder, we don't have to worry about that here. And then we have our x squared plus x minus 6 outside. So when we do our long division, we're going to ignore everything except for the leading term on the outside. And we're going to say x squared times what is going to give me x cubed. So in this case, that's just going to be an x. So I'm going to write x up top, and I'm going to put it over the x, so everything lines up properly. That was our dividing question. Now we do multiplying. So I'm going to multiply x times the entire divisor. So x times x squared is x cubed. X times x is x squared. And x times -6 is -6x. Okay, now we did the multiplying, now we do subtracting. So for subtraction this time, I'm going to change the sign of everything. So this is negative, negative, positive. X cubed minus x cubed, poof, go away. 4x squared minus 1x squared is 3x squared. Negative x plus 6x is plus 5x. And then we bring down the -4. Okay, now we repeat. So x squared, because we're ignoring all this other stuff, x squared going into 3x squared. Just need a 3 for that. So I'm going to do plus 3. And then we multiply through. So 3 times x squared is 3x squared. 3 times x is 3x. And 3 times -6 is -18. To subtract, we're going to change the sign of everything. And the 3x squareds cancel. We get 2x. And 4 from 18 is 14. All right, so this is our remainder in this case, and this is our quotient. Remember that you ignore the remainder. So we don't care what this remainder is. All we're going to look at is the quotient. So this, because this is not a horizontal line, because it has a slope of 1, this is going to be our oblique asymptote. So we have an oblique asymptote of y equals x plus 3. And there we go. So that's how we can find our horizontal and oblique and vertical asymptotes. All right, so now that we've finished these examples of finding horizontal and oblique asymptotes and vertical asymptotes, we just have one more thing to do for this video. We're going to state a few facts about asymptotes to kind of wrap everything up, tie it up with a bow, and then we'll be on our merry way. So let me take a moment and write some interesting facts about asymptotes up on the board for us. All right, so we have 4 facts about asymptotes that we're going to look at. I'm going to stay out of the way for a moment in case you want to pause and copy these down. All right, so let's talk about them. So this first fact says that if the degree of the numerator is larger than the degree of the denominator by 2 or more, then you're going to have a nonlinear asymptote. So basically what happens is when you do that long division, you're going to get like whatever the difference in the 2 degrees is going to be the degree of whatever your asymptote is. So if you have like x to the 5th, blah, blah, blah up top, and x squared, blah, blah, blah on the bottom, when you divide that, you're going to get an x cubed, blah, blah, blah. So you'll have like a cubic function as your asymptote. So in this class, we're not going to worry about anything that's nonlinear. We're just going to focus on oblique and horizontal lines for our asymptotes of that form. The second note here is your rational function will only have one of that type of asymptote. It will have either one horizontal, or it'll have one oblique, or it'll have one nonlinear asymptote. However, it can have however many vertical asymptotes and however many holes it feels like having. So you can have multiple vertical asymptotes, but only one that's of the horizontal / oblique variety. Now, when we go to graph with these asymptotes, a rational function will never ever cross over its vertical asymptote. This is because the vertical asymptote is happening because that x value is not in the domain. So we can't cross over it because the x values doesn't have a defined y value for it. So we'll never like draw over the vertical asymptote. However, number 4 says we might cross over the horizontal or oblique asymptotes. This is because the horizontal and oblique asymptotes are describing end behavior of our rational function. So in the middle, we're more likely than not to cross over that asymptote, the horizontal or oblique one, and we're going to get closer to it on the ends. So it is wrong to say a function never crosses its asymptote. It could. It's never going to cross its vertical asymptote, but it could cross its horizontal or its oblique asymptote. And I'll leave you in suspense there because we're going to do some graphing in the next video. For this video, that wraps it up. So I hope this video was helpful to you in identifying the holes or asymptotes of rational functions. And as I mentioned in our next video, we're going to start graphing rational functions, put all this stuff together. So I look forward to working with you through that. In the meantime, I hope you have a wonderful day. Bye for now.